Hello everyone. Today we'll be demonstrating our Signals, Networks and Systems mini project, which is on the topic of noise cancellation. This project is done by myself, Aarush Maheshwari, and my two friends, Rounil Mahato and Arnav Kedare. The project is done under the guidance of our professors, Professor Najib Gatte and Professor Shanti Swami ma'am. Firstly, what is noise cancellation? Noise cancellation is the process of removing unwanted noise from a signal, usually with the aim of isolating a desired sound or signal. This technique is most commonly used in applications such as audio communication, signal processing, and active noise cancelling headphones. The process works by identifying and subtracting the noise component from the signal to improve the signal to noise ratio and enhance the clarity of the desired signal. Now, how does this noise cancellation work? There are two primary methods of noise cancellation, which are active and adaptive noise cancellation. Active noise cancellation uses the principle of destructive interference to cancel out unwanted sounds, typically in real-time applications such as headphones. For noise detection, it uses a microphone which picks up ambient noise from the environment. The signal processing is done by inverting the noise signal by a phase shift of 180 degrees to create an anti-noise signal. This anti-noise signal is then combined with the original audio signal. And then destructive interference takes place when the anti-noise signal and the noise meet. They cancel each other out due to destructive interference, which significantly reduces or eliminates the noise. Active noise cancellation is generally effective for low frequency and consistent sounds such as the engine hum or the fan noises. Higher frequencies are harder to cancel due to their more complex wave patterns. Secondly, the adaptive noise cancellation techniques. In applications where noise patterns are more variable, such as speech enhancement, adaptive noise cancellation is used. This approach relies on adaptive filters that adjust the parameters in real time based on the characteristics of the noise. The desired signal is a signal that includes both the desired audio and the noise. The noise reference signal is an additional microphone or source that captures only the noise. This signal is used as a reference to help remove the noise from the desired signal. Adaptive filter. An adaptive filter such as the LMS, which refers to least mean squares filter, processes the noise reference signal and learns to model the noise component present in the noisy signal. For error minimization, the adaptive filter continuously adjusts its coefficients to minimize the difference between the noisy signal and the output, effectively cancelling out the noise component in the process. Adaptive noise cancellation is particularly useful in environments with non-stationary noise, which is the noise that changes over time because the filter adapts to the changing characteristics of the noise. What are certain applications of noise cancellation? Noise cancellation is mostly used in audio and communication systems, for noise cancelling headphones, and in certain medical as well as industrial applications. Some advantages of noise cancellation are improved clarity of the desired signals, enhanced user experience in audio devices, and reduction of health risks related to constant noise exposure. Certain challenges related to noise cancellation are that high frequency noise can be difficult to cancel effectively, and it requires precise timing and phase adjustments. One of the methods of practicing noise cancellation is displayed by this Matlab code. It focuses on a signed data LMS algorithm, which refers to least mean square algorithm, which modifies the filter based only on the sign of the input data. This code creates a sinusoidal signal and adds random noise. The noise is filtered using a FIR filter with a specified cutoff frequency. The breakdown of the code is as follows. The first line generates a sinusoidal signal which has a frequency of 0.055 Hz. The 2 into pi into 0.55 defines the angular frequency, and the 0 is to 0999 refers to the step size. The step size of the signal. The second line, which includes noise, is equal to RANDN, which is an inbuilt MATLAB function, is used to generate a Gaussian noise signal of length 1000 with a mean of 0 and variance of 1. The filter DSP.FIR filter creates a finite impulse response or the FIR filter using MATLAB's DSP.FIR filter class. The filter numerator is equal to FIR1 sets the filter column filter coefficients or the numerator of the FIR filter to those which are generated by FIR1. FIR 11, 0.4 creates a low pass filter of order 11 with a normalized cutoff frequency of 0.4. F noise is equal to filter dot noise applies the FIR filter to the noise signal, generating F noise. This then filtered noise will have reduced high frequency components due to the low pass FIR filter. D equal to signal plus F noise adds the filtered noise to the original noisy signal D that we have to clean. Coefficients equal to FILT dot numerator. Adjust the coefficients by subtracting 0.01 from each coefficient and transposing them to match the shape required by the LMS filter. MU is equal to 0.05 defines the step size of the LMS filter, which controls the rate at which the adaptive filter updates to minimize the error. The next line creates an LMS adaptive filter using filter object using the tsp.lms filter inbuilt function. It specifies a filter order of 12 and uses step size mu to filter the updates. The next line applies the LMS filter to the noise signal with D as the desired signal, and the output signal is error signal E, which ideally represents the original signal without noise. L equal to 200 indicates the number of samples to the plot. The next line plots the original signal and the error signal E for the first 200 samples. This comparison visually shows the effectiveness of the noise cancellation. The next few lines are just given as labels or titles, which can be indicated in the graph as shown. This is the output waveform of the noise cancellation, which has been done using signed data algorithm. The blue waveform indicates the actual signal, and the red waveform indicates the signal which has been created as a result of noise cancellation. Now, my friend Arnav will demonstrate a few more codes on how to practice noise cancellation.
So we'll see the second code, uh, which depicts the sign error LMS algorithm. It is a variant of LMS algorithm where the update rules uses only sign of the error rather than error's actual value. This often makes its whereabouts more robust to variations in error. So I will start with the explanation of the code. So first, a signal is generated as we have seen in the sinusoid, as we have seen in the LMS uh, algorithm, and a random noise is used in this algorithm for filtering. Noise filters through an FIR filter with a cutoff frequency of zero point 0.4, which is normalized. The filter noise is added to a signal to simulate interference in the observed signal. A desired signal is generated, which is the combination of signals that we aim to clean using the LMS algorithm. To filter the coefficient, initializing the filter coefficient slightly, which are altered from the FIR filter's numerator values. It also sets the step size for the LMS algorithm in the second code. The LMS algorithm here creates the filter with sign error LMS method, and the initial coefficient, the sign error method adjusts the coefficient based on the error. So we will go to the plotting results. So this filter first plots the first 200 samples of both original signal and filtered error signal to observe the noise cancellation. The plot shows the original signal overlaid with the noise cancelled signal. Ideally, the error signal, which should closely resemble to the original signal after the noise is minimized. So we will look at the further code about an NLMS algorithm implementation. So similarly to the previous algorithms, this NLMS algorithm system depicts a slightly different method which can be used to noise cancel a certain input. So we will go through the code step by step. So in the first step, we see that a sinusoidal signal is generated again, and a Gaussian noise is created, which is passed through a low pass filter FIR to simulate filtered noise. The desired signal D is found by adding filtered noise to the original signal, creating a noisy signal that the NLMS algorithm will aim to clean up. So we'll know about the filter algorithm which comes after this. An FIR filter, FILT, is created with a specific numerator based on a 11 tap FIR filter with a cutoff of 0.1, 0.4. The filter coefficients are initialized and are slightly modified for initial conditions in an LMS algorithm. The step size for LMNS is 0.1, which controls the conversion rate of a filter. The LMNS first filter application displays object in configured to use normalized LMS method with a specific step size and initial conditions. The filter processes the noise and D signal, returning an error signal E that represents the difference between the desired signal and filtered output. In the plotting results, we can see that a segment of original signal and error signal after noise reduction is plotted to observe the effectiveness of an NLMS signal. So I would like to say to my friend Ronan to continue the fourth program after this.
So this code performs noise cancellation using an adaptive filter to process a combined signal of multiple sine waves with an added Gaussian noise. Now, here is a breakdown of each part. So the first part is the parameter for signal generation. Here the fs is sampling frequency, which is 1000 hertz in this case. The line t, which is given here, creates a time vector t for signal generation. So in this, as you can see in this particular section, it 0 semicolon triple nine, it creates a row vector of integers from 0 to triple nine. This number represents sample indices over a 1 second period if sampled at 1000 hertz. And the apostrophe mentioned here transposes the row vector into a column vector, and this is done to match the convention of vector in signal processing uh, to make it compatible with most Matlab functions. And the divided by fs is used to because it converts the sample indices into time values in seconds. So since fs is 1000 hertz, and if we divide it as 1 divided by fs, it came out to be like 1 ms. So the resulting time vector t goes from 0 to 0.999 seconds in increments of 0.001 seconds. Now, from moving on, here we create original signals. So three separate sine waves, signal 1, signal 2, and signal 3, with frequencies of respectively 50, 120, and 200 Hz are generated. And the component original underscore signal, in which all the signals are combined by adding them, as you can see. After then, we add a noise. So Gaussian noise is generated with lower amplitude 0.5 and added to original signal to create noisy signal. As you can see, both are added, simulating real world signal corruption. And then in this, you can see the RANDN function Matlab, which creates random numbers following a normal distribution, that is mean equal to 0 and variance equal to 1. And here the length t represents the number of elements in t, which was 1000 as earlier discussed. And this whole section specifies the size of the output from RANDN function, where length t indicates the number of rows and 1 indicates a single column. So overall, it simulates Gaussian noise that will be added to original signal to create a noisy signal. Then after that, we create a FIR filter. FILT is a finite impulse response, which is defined using DSP.FIR filter. Here DSP stands for digital signal processing and refers to a set of specialized tools and functions provided by DSP system toolbox, and which is widely used in areas such as audio processing, communication system, biomedical signal processing, and control system. Then here FIR1, in this it creates a 31 tap FIR filter with normalized cutoff frequency of 0.4. And moving onwards, the next thing is adaptive filter setting for the LMS adaptive filter. So we have given MU, which sets the step size for LMS, which is mentioned below, like used in DSP.LMS filter, which is 0.01, and the order of the adaptive filter is 32, determining the number of filter coefficients. Then in the LMS DSP.LMS filter, it initialize an adaptive filter object with LMS, sorry, an algorithm setting, uh, and the in this, the LMS noise, comma noisy underscore signal, the adaptive filter is applied to the noisy signal, aiming to reduce the noise component. Error underscore signal represents a noise cancel signal. And when we call in this the LMS filter, it returns the error signal component, which is basically the difference between noisy signal and estimate noise. Uh, and the LHS represents the symbol, this, which is also called tilde, is used to ignore the first output, sorry, and the error underscore signal captures the second output, which is the error or difference between noisy signal and filter noise estimate. Now we are going to observe the plotting and the result of the output. So I'm going to just run this code, and here it comes. So the first we plot the original signal, which displays the combined signal of 50, 120, and 200 sine waves. And then we plotted noisy signal, which shows the combined signal with added noise. And then third one is noise cancel signal, which plots the result after applying noise cancellation with adaptive filter. And the fourth is comparison plot, which compares the original signal with noise cancel signal for a visual assessment of noise reduction. Thus, the main objective here was to observe how effectively the adaptive filter removes noise from the original signal by comparing the error signal with the uncorrupted original signal. So next on to conclusion of the whole project. This set of Matlab code segments demonstrates noise cancellation using adaptive LMS algorithms on signals combined with Gaussian noise. Each segment follows a process where a clean sine wave signal is generated and noise is added to simulate real-world interference. An FIR filter shapes the noise before combining it with the signal, making the setup more realistic. The LMS algorithms are then applied